right? That's my estimate of the true slope. Roughly about half-ish. That's what I'm estimating. So what? So okay, I'm a statistician. We are the ultimate Eeyores. Anybody is happy, we come along and we make them sad. All right? So here you are, and you're very happy because you have estimated a slope based on your random sample of points, right? And this line has some slope. You know how your estimate is going to change. And this is what the statistician always looks like. Like, really? That's what we look like. Okay? And the statistician says, well, wait a minute. What if your sample scatter diagram had some slope? But that's not what the actual one was. In fact, the really scary thought is, what if the true line is actually flat? Okay, let's see, what if Tyche's true line was actually flat? Yes? Forget about the errors. No matter what x is, wouldn't y be exactly the same? Flat line? Yes? So in fact, there's no genuine linear relationship between x and y. Yep? There's no correlation whatsoever. Right? So there's actually nothing there. So what if her line was flat, but the points came out in such a way that you think there's a slope? Right? So let's see what happens if I'm going to actually do okay, I'm going to take a situation in which her line has slope 0, and why don't I say intercept 10, and let's look at 25 points. Okay, and let's see what happens. Okay, so that's her line. That's the true line, and she's given me 25 points. Here's what I see.
Which line is that?
I'm sorry?
Which line did you put? 0, 10?
Slope 0, intercept 10, and I chose 25 points. Okay?
We have
Yep.
to input that at this point because it's
Yeah. I'm just, yeah. So, okay, this is what I saw. Now, what you're going to see is something different. But anyway, this is what I saw, right?
Yeah.
So I do what I do, and I put my line through it. What do you see? I'm putting this nice positive slope, right? You give me bigger x, I'm going to give you bigger y. I'm feeling very proud of myself.
It turns out negative.
Yeah, mine goes
But
down.
it goes down, not up.
No, it's
No, but everybody's going to get something
everybody's
different.
Oh, I'm sorry.
Yeah.
Right?
Yeah.
Everybody's going to get something different because there's actually nothing going on.
Okay.
And we're all saying rubbish,
Yeah.
right? Just different rubbish.
Yeah.
Yeah?
It's really nice.
Yeah, yours is there.
And so, well, the truth is the flat line, and here I am saying, well, woohoo, I got a slope. That's bad news. Right? I shouldn't be doing that. Right? And so now the question is, how do you protect against that? Well, you go back. So that is the reason for this question. Right? What if there was actually nothing going on, and but your picture says something different? Well, what I'm going to do is I'm going to go back to my estimated slope. Right? My estimated slope is around 0.4 to around 0.55. You agree?
Mm-hmm.
You seeing a 0 in there? You seeing a 0 among your estimates at all? You're not, right? So you're 95% confident of this interval, right? There's no 0 in there, right? That is a way of testing whether or not your slope is 0. Right? So the classical hypothesis test true slope equals 0 versus true slope not equals 0, right? A lot of the computer packages will print out a p-value based on some t-statistic, right? This is that, but done hands-on, right? And you don't see a 0 in there. You can reject the null hypothesis of 0, right? And I made a 95% confidence interval here, right? So your p-value cutoff for your test would have been 5%. And there's, there's discussions we have our students. If you wanted to work at the 1% level, you make a 99% interval, and so on. Now, notice, this is better. This is better than doing a hypothesis test of is the slope 0 or not. Because this not only tells you the slope is not 0, it tells you we think the slope is between 0.44 and 0.56. That is much more useful than just saying 0 or not. Right? So we tell students that if you are testing for a number, right, is that number equal to 0 or not, or is that number equal to 98.6 or not? Right? Just estimate the number. Right? Make a confidence interval and look to see whether that value is in there or not. Right? Then you have answered 2 questions. Right? You have answered whether that is a plausible value, and if not, then what are the plausible values? You have answered that. So we encourage students to do inference in this way. Okay? All right. We've had a whole day on regression, and I am actually going to pause and take a few questions, and then we're going to clear our heads, and we'll show you what we do with classification. Yes?
This is either off the mark or jumping ahead. You had multiple potentially influencing factors in the original table. We've only looked at a small sample of that. What if there are other factors that are actually relevant here? Can we bring them into the picture, and is that going to be something that we would teach today, or you'd want to do it at another time?
That is not something that we would teach in Data 8 because of the many issues that are involved and the finite number of lectures that we have, right? The next class, however, Data 100, Stat 131A, all of these are follow-on classes. All of them start with that, right? So there are all these variables that we could have used as well. Now, one of the things I'm about to do, though, when we do classification, is we'll use multiple attributes to classify.
Thank you.
Yeah. More questions? Yes?
So for like the warnings about your sample may not look like the person you're trying to predict, do those warnings come up just in the abstract, or do you show them what can
Labs and homework. Right, so we use those to make many points. So homework and lab is not just an exercise in what they have done, but we've tried to choose the questions so that every question makes a point. So I went through last spring, this past semester, I went through every week with 2 of the lead GSIs, looking at the entirety of what the students had to do the following week. How is the homework connected to the lab, connected to the lectures? And to the discussion, so when is the student learning what? Why are we emphasizing this and not this? So we use the exercises to make those points. So some of the times we will demonstrate something in lecture. But really, when we devise courses, we spend a lot of time thinking about what we are going to say and how we are going to say it. But the student learns what the student does. Right? So we have tried to pay a lot of attention to what we are asking the students to do. And we can do much better in that. So that is going to be my job over the next year, is to look not at what we are giving the faculty to do, but what we are giving the students to do. Right? That is the crucial thing. So we try to use that.
Can I ask just a logistics question on Data 8 versus Stat 2, Stat 21, Math 1A, Math 10A, Math 16A? I mean, are a lot of students taking both of these? So do you think there's a reduction in, I'm just, as an advisor, I'm just dealing with a lot of the students, and I mean, we don't have Data 8 fulfilling any math requirement right now, and it doesn't fulfill the math requirement for med schools. And I'm just curious.
It will.
You think it will?
Definitely.
I mean, I'd like it to, but I mean, we need to make that happen if that's
So-
going to happen. I mean, it took us like 4 years to get Math 10A and 10B to fulfill the requirement. So that took us 4 years
So
of us making an effort to make it
David
happen.
Culler is no longer here,
Oh,
but
he's not here.
he and Catherine
Carson.
were instrumental in talking to many of the departments that had a statistics prerequisite for their majors.
Right.
And all of those, I would say over, I think some number, like 97% of those departments immediately included Data 8 as a way to satisfy the requirement.
Equal to
Equal
Stat
to
2.
Stat 2 or 20 or something.
2 or
In
20 or
some
21.
economics, naturally needs more mathematics,
Right.
right? So economics requires Data 8 as well as Stat 88, which is
Okay.
the theory supplement, and so on. So I have little doubt that this will become a part of requirements.
Has
Now,
Stat 2 gone down in enrollment?
Stat 2 has definitely got down in
Okay.
enrollment. Stat 2 is an introductory statistics course where you do this, all of these ideas,
Right.
but you do it on a hand calculator, so you don't have the big data sets, and you're not doing this, and so this is work, right? The hours that a student has to spend. If a student wants to spend fewer hours and get their breadth requirement done in a way that kind of makes sense to them but is not too demanding, they take Stat 2. Stat 20 has been redesigned. Stat 20 now does something like this with R.
Stat 20 now has R in it.
Uh-huh.
And
That's new,
Gaston
right?
Sanchez was here, who had
Yeah.
taught it one of the times and helped the Rification. He was here the first couple of days.
Yeah.
Thank you.
More questions? Yeah.
There's only one piece of jargon that you didn't explain, which is when you said the error. What are you saying when the student asks you what the error is in this simple?
Which I talked about a lot of errors. Which error?
The error at the regression line. Okay.
The error from the regression line.
What do you say to a student when they
Okay,
get
so the thing that I will tell the student is that this is a picture, and there are two axes. So the vertical axis is something physical. I always use dollars, income as the example, right? So there's an actual amount of dollars, and there is a predicted amount of dollars, and the error is simply the difference between those two. It's a vertical difference between those two. So corresponding to every line, a point has an error, right? The errors of the regression line are very particular. The ones that you observe, they are called residuals, right? They're the ones that have the smallest mean square among all that you could have got. These errors, the ones in the model, are abstract, right? Abstract model is a difficult thing for students. You're right to point out that it's not just the errors, it's the fact that there is an imaginary line, right? That is very difficult for students. And so we have tried, as far as possible to have the models be actually physical, right? So you have a population of 26% black people and 74% not, and you're picking people. Well, actually, it wasn't people, it was men. It drives me insane. Okay, 21-year-old or more, you're picking physically. The student can imagine that. But we take care that the next example is Mendel's pea plants, where his model is that each pea plant has 75% chance of being purple flowering independent of all pea plants. And this is an abstraction. So we try. It's a difficult thing. We ready? Shift gears?
Mm-hmm.
Okay. So let me remind you about classification. It's a prediction problem. Okay, test whether there is really a slope. This is what I said. Okay. So classification is a prediction problem. In data 8, we just do binary classification, right? An individual is in one of two classes, a yes or a no, and we are going to look at attributes, and we are going to predict whether the person is a yes or a no. And this is used in lots of places. When you're shopping on Amazon, Amazon needs to know that whether the transaction you are making is fraudulent or not, right? So based on all your past history and the history of similar people, it is going to make a prediction about whether the transaction is fraudulent or not. And many of you have been to other countries and tried to do some transaction in your credit card, and you get a text message saying, is this really you? Right? That is a machine like this trying to check whether it's you or not. Okay? We will do a medical example. We can use these methods not to replace the medical professional, but to give them another tool that they can use. So the example that we're going to do is an example where we have pictures of clumps of cells, and we are trying to predict whether cancerous or not. One of the examples I like is this one. All of these dating apps, right? You put in various criteria, and they tell you whether you should be matched with this individual or not. Yes, one of the things I keep trying to remind people is all of this stuff that you think is brand new. You go online and you do stuff. These dating apps We've had dating apps for millennia. Right? They were just called aunties.
Parents, yeah.
Right? I mean, who knows every attribute of everybody, right? And will look at your attributes and say, oh, you should be with that person and not with those people. Those are the apps, right? And so it's been happening for a while. We've just automated it, right? And machine learning is because we have so much data now, and we need it so fast that you log on to anything, and somewhere somebody knows that you were searching for shoes yesterday. So even if you are trying to log on to something else, you will see shoes popping at you, even if you bought the shoes, right? And it's all happening within a split second, right? So some machine has done a very rapid fire calculation somewhere, and also has asked a bunch of vendors, do you wish to flash your ad to this person or not? And somebody has said yes, and you've seen that ad. It's all happened rather fast. So machine learning is going on rather a lot. We're just replacing what we used to do by hand, by machines, and there is an enormous power in that. With enormous power comes enormous responsibility. And so at this stage of the course, I asked David Wagner to come in and give a 50-minute lecture on privacy. Right? It is a very serious and beloved lecture. You should please all watch it. Go on to data8.org, find the spring 2019 site. If you look at the calendar, there is one day that says privacy. Please watch that. Right? Because the students, before they do any of it, they need to understand what they are holding in their hands and what they are charged with. It is not just simply to blindly compute.
He did it here on Monday,
Oh, good. Excellent.
right?
Excellent.
The police license plates.
Oh, good. Yeah, but I mean, more than that. I mean, he talked to people about Cambridge Analytica and so on and so forth.
Okay.
You know, the issues that are involved and the perspectives and so on. And so it's really important for our young people to hear that
Wow.
before we do any of this. Okay? So what I'm going to do in the interest of time is I am just going to move to, another notebook. Lecture 4, Summer 19. Okay.
Different notebook now.
Lecture 4. Summer 19.
I'll wait until people have got it. Lecture 4, SU 19. You see it?
What's CKD?
I'll say in a minute. I'm just waiting for people to get the notebook.
Okay.
What's that one?
Everyone there? No?
Yeah.
Everyone? Okay. So here is a data set. It has 158 rows. Each row corresponds to a patient. And what we are interested in is this final column called class. 1 says they have chronic kidney disease, CKD, and 0 says they don't. All right, so this is a historical data set that we have of 100 and however many patients. And we have all of these attributes. And I do not pretend to know, well, I understand age. And I understand some measure of blood pressure, but then there's a whole lot of other attributes, right? And now along comes this new patient, and we have to make some prediction, chronic kidney disease or not. And the assumption is that we can measure all these attributes. Okay. So what we're going to do is we're going to start simply, and we're just going to look at, first one we look to see how many there are in each class. In this data set, 115 people did not have the disease, and 43 people did. Okay, what we're going to do is we are going to draw a scatter diagram of 2 of the variables. So each point represents one of the individuals. On the horizontal axis, you have the white blood cell count, and on the vertical axis, you have the measure of glucose. The color of the point represents whether or not they had chronic kidney disease. All right, now the gold points did and the blue points didn't. Right? So now if a new person comes along and their point is somewhere here, right? So this right here, what is going to be your prediction? Disease or not disease?
Disease.
Disease, because they're right in the heart of the yellow zone. Right here.
Of course.
Yes?
Yeah.
And if they are here, you're going to want to predict no disease, maybe you're a little bit worried because there's a little bit of overlap here, so you may get things a bit wrong, right? But there seems to be some separation. And so what we're looking for are variables that helps us sort out these two classes. Okay? And so we'll do another one. Hemoglobin and glucose.
Better.
People with no disease, people with disease. Okay? So if a person comes along and their hemoglobin glucose point is here, what are you going to predict? Disease or not?
Disease.
Disease. Why? Because you are using that approach that we had right in the beginning, which is we are going to find people who are similar, right? And then our prediction is going to be what's typical for that similar group, right? And in this case, that similar group is entirely gold by any reasonable method, reasonable definition of what is similar, right? You should be predicting gold, right? And if the point was here, you should be predicting blue. And so that's the thing that we have to now automate. And there are all kinds of decisions that we have to make about, what is similar, and how many people are we going to take, and so on and so forth. But what we are going to do is called nearest neighbor classification. We're going to take our new point, which is, I'm just going to put that right here. It's the 10 to 100 point. Okay, we're going to take our new point. We're going to find the nearest neighbors, some number of nearest neighbors, which we get to decide. And we're going to take, our prediction is going to be the majority class of those nearest neighbors. Now, we will do well if the attributes that we have chosen are such that the two classes are actually separated by these attributes. Yes? If we choose attributes so that the scatter diagrams are a mess, yes, then you're going to have trouble making your predictions. All seem reasonable?
Yeah.
Okay. So we have shown you these are. I'm just looking at two variables. Now there were many other variables. We could look at all of them at once. It's a little hard to see in the picture. But what I'm going to do is I'm going to show you a data set on banknotes. So these are 1,372 banknotes, and the 0 is it's not fraudulent, and the 1 is it's fraudulent. Right? It's forged. Okay. Now, all of this is done by pictures of the banknote. You have to look at the banknote and say whether it's forged or not. This is where you need the domain scientist, just as you needed the medical professional to tell you what are the variables, the attributes that you should be measuring. Right? So you need, and what the vision people have done is that they have calculated numerical quantities to do with these banknotes. And as a statistician, I notice variance, skewness, kurtosis, and entropy. So they have calculated numbers to do with this, and we are going to see if we can use their numbers. We're going to see if we can use their numbers to identify the class, and we are going to try to forget that we are intelligent, thinking human beings. We are going to be the machine. The machine doesn't care where those numbers came from. The machine doesn't know whether it was right or wrong or good or bad. It's just some dumb number. Right? So we're going to think like that for a second. And I am going to draw you a scatter diagram of these banknotes using the variance on one side and kurtosis on the other. Yeah, kinda. These things are mostly not fraud, and these things are fraud, but then you have a mess over here, right? So we try something else. And these beautiful dolphins. This is skewness and entropy. Yeah, you can kind of separate. Yep. But we have lots of variables, and so I'm going to do the most that I can, which is give you a three-dimensional scatter diagram. So we have the skewness, the variance, and the kurtosis. And this is a three-dimensional picture, and that sure looks like you have a separation there. Yes, and I'm going to try something. You don't have this. Give me a moment. I did this in class. Here we go.
No, we don't have it.
You don't have it. Okay, you agree this is the picture that we just saw?
Yes.
Yes? Okay, I'm going to try something else. So this is the same picture. Wish me luck here. You see, you can almost put a sheet of cardboard through that, right? You're going to get this classification right almost always if you use these three variables. Yep. Now the thing is, of course, we have been looking at this and finding things. The machine is not going to look and find things, so we have to automate this process. Okay? And so let me pause for a second and take some questions, and then we will get to actually doing this. Yes?
I'm trying to formulate this question, so bear with me. Isn't it imaginable that some of these factors that apparently play a role here could be more important than others? That there could be. I'm sorry.
Totally.
Okay,
It's
so
imaginable.
at this point we don't have a way to discover that. It could be that, for example, two of them work the same way, and it doesn't really matter which one you pick. I mean, that's imaginable at any rate.
Totally. That is why I don't do multiple regression in data 8. I don't have time to talk about exactly this. Do not use the person's height as well as the length of their leg. Right? Use one or the other, and they kind of carry very similar information.
Yeah, exactly.
Right? So all of this is true. All of what you are saying is true.
More of a theoretical question. Why isn't this also regression, where your outcome is a binary, like a logit?
You could certainly do logistic regression in this case. We happen not to be doing it in this instance.
So when you teach classification,
Yes.
you don't teach it as must be done this way. It's an alternative.
Totally.
Okay.
Yes, it is another way to make predictions.
Got it. Thank you.
Right? So we want students to go out on data 8 realizing that it's a rich world out there. And that they can do a few things quickly that will get them some interesting answers, but there's a lot more going on. Yeah, it's presented as an alternative method. Okay. So back to your notebook. Actually back to the slides. Okay. So what we're going to do is called training a classifier. A classifier is a rule. You give me a new person, and I will split back to you either a 0 or a 1. Right? So it's essentially a function. It's an assignment of 0 and 1. And we are going to use the attributes of our example, this new person, and we are going to feed it into our classifier, and we will get a prediction, that is a 0 or a 1. That's what we're going to try to do. Okay, what we are going to use is called nearest neighbor classification. We are going to look at our point. We are going to identify the points in our historical data set that are closest to this point in some sense. And then we are going to use the majority class of those close points. Okay? To make our life easier, we are going to look at an odd number of nearest neighbors. Right? Either the nearest neighbor or the 3 nearest neighbors or the 5 nearest neighbors or 7, because there will always be a majority class and we don't have to be fussing about ties. Right? So when you see k nearest neighbors classifications, k is almost invariably odd. Right? We're going to do a majority. Now, if you think about extending this to situations where you don't have just 2 classes, but maybe 3, right? Then you have to be a little bit careful about what you do at the end when you have the classes of your nearest neighbors. How do you pick which one you are going to use, which one is most common, how do you break ties, and so on and so forth. I'm not going there. Right? I'm just dealing with a 0 or a 1. Okay. So the historical data set is an important clearly I decided to do this later. Let me just make a general point. I have a historical data set. I have a new point. I'm going to use the historical data set to classify my new point. All of what we said for regression applies. That new point better be like the historical data set. Right? If they are not, that historical data set doesn't actually apply to your new point. And there's no amount of fancy stuff that you can do with your learning algorithm that is going to avoid that, right? So checking that your model holds is a very good idea. Okay, so what we're going to do is we are going to look at data that came from Brittany Wenger, who won the Google Science Fair in 2012 by taking pictures of clumps of cells and identifying whether or not they're benign or malignant breast cancer. And there you can see she's meeting famous people and so on. Right? Okay. And so let me see. Okay. So here you have her data, and she had about 675 or so clumps. And she has many variables: clump thickness, uniformity of size, shape, adhesion, etc., etc., etc. And in the end is the crucial variable: 0 for benign and 1 for malignant. These are her data, right? And what she's going to do is she's going to use these data to classify a new point. So I'm going to look at a scatter diagram as we did before of bland chromatin and single epithelial cell size, and here I am reading that as though I am reading a foreign language. But I don't actually know what those variables are. I am a machine. Okay, and now look at that. That does not look like 678 points. And why not? Because, well, a lot of those were in the same spot, right? Why were they at the same spot? Look at the data. The data, they're all on a scale of 1 through 10. This is a technician who has viewed the clump and has jotted down numbers. So in some sense, they're all categorical, and I get a little bit of the heebie-jeebies, but anyway, they're all on a scale of 1 to 10. It is very, very helpful to us as a first example that they're all on the same scale, because distances are very much affected by the size of the individual numbers, and the fact that these are all on the same scale means that, you know, just from a computational perspective, no one variable is more important than the other, right? So I'm just going to cross my fingers and go with it. Okay, so what David Wagner did was he jittered the data for you, and kind of now you can, so there aren't actually points all over here, there's just a bunch of points here, he's just showing you the points. Right, and it is apparent that if you use just these two variables, you do have some fair separation of the two classes, and the hope is that if you use more, you might actually do better. We don't know, but we can try. Okay? Okay. So, really, the program is pretty simple. There's going to be some new data point, right? Some new picture. And that is going to be classified by the technician, but it will not go through whatever biopsy procedure to decide whether it's benign or malignant. We'll just have the data that you get from the pictures. And our job is to see if we can take those numbers and say, is this a 0 or a 1? So what do we need to do? We need to say, which of our points is this close to? Yeah? So we need the distance between the attributes of our new person, or the new clump, and all of the other clumps that we know. Yes? So we need the distance in multiple dimensions. Right? We have a lot of attributes here. Right? So x1, x2, x3, x4, etc. And then our historical point has all of those attributes as well. Right? And we need to find the distance between these two points which are in multidimensional space. So what I do in data 8 is I say, look, supposing we just had 2 points. You know how to find the distance between 2 points. You use Pythagoras. Yes? And the lovely thing is that you can just extend. So Pythagoras says you have 2 points, x0, y0, and x1, y1. Right? You look at x0 minus x1, that's the first difference, and y0 minus y1, that's the second difference. Square the differences, add, take the square root. Yes? Mm-hmm. So the mathematicians will hear L2 norm, whatever. You will Yeah. So we just tell them, look, you got to do this in multiple dimensions. Fine, just add the squared differences of everything else. Right? And they're totally happy to believe that that is the way to calculate distance in multiple dimensions. Right? It works in one dimension, it works in two dimensions, they just don't want to bother, they'll accept that it works in multiple dimensions. So we do have to tell them that. Then the job is easy. You have one point, you have her 678 whatever, 680 something points. You calculate the distance between your point and each one of her points. Yes, you're a machine. Yeah, you just do the whole lot. You find, let's say, the 5 that are the closest. Yes? And you see what classes they had. That's what we're going to do. And so today I'm going to ask you to just glance over but not focus on code. Just notice what I'm doing with the students. Write all of this. So we have taught them, when you have a big project that you have to do, right? Forget the notebook. Get an actual notebook and write a bullet point sequence of moves that you have to make. Sketch out what you have to do. Plan. And then build in little bits. Don't write one enormous, great, long program, right? Write little programs, each of which is interesting, and then put them together. Okay, so distance. 0.1 minus 0.2, right? You're finding all the differences. Yes?
Mm-hmm.
You are squaring. Yep. You are adding up. Yes? That's what Pythagoras tells you to do, and in the end you take the square root. Yeah?
Mm-hmm.
Okay. So one of the things I'd like to point out, this is a computational note, is that in a table, each column is an array. Right? An array is a sequence that has all variables of the same type, right? It's the same attribute. But each row need not be. Right? Each row is the attributes of one particular person, and as you saw with our mother-baby pairs, there was gender, there was whether or not the person is a smoker, etc., etc. Yeah. So the row is actually not an array. But since these rows are all numerical, you can convert them into an array. And so the student does have to pay attention to types. We are very particular about that because they have to imagine the right thing, right? So this is how you find the distance between two arrays. But you're actually going to have rows of tables, right? Those aren't arrays. So you convert them to arrays. And then you find the distance between those using the distance function that you wrote.
And that's the difference between people or cases.
That is the
whatever it
difference
is.
between two individual clumps. Yes. Okay.
It's random what row they're in, right? There's no.
Yeah, so this is just, I have two rows, and I'm finding the distance
There's
between them.
difference between
Now
each
I
one.
have to decide which two rows.
Yeah. They're just
Yeah.
random between
Okay.
all different rows.
So I will define this function. And now I am going to, so in fact for the historical data sets, I actually have everybody's class. But I'm going to pretend I don't. Right? So I'm going to drop the class column, and I'm going to just look at the attributes. Right? So there are 683 of these. Yep. And I am going to use my distance function, it's called row distance, just to calculate distances between rows, just for us to get a little bit of a concrete sense of what's going on here, right? So I'm going to calculate the distance between row 0 and row 1, okay, using the function that we defined, and I get 11.87, and I have no idea what that means, right? I have something, it's a number, right? So now I am going to compute the distance between row 0 and row 0. What should I get?
0.
I should get 0. Every time I write any distance routine, I always do this as a check. Right? How I messed up somehow. And now if I look at distance between row 0 and row 2, I have 2 and a bit compared to row 0 and row 1, which was 11 and a bit. Row 0 is closer to row 2 than it is to row 1. That's what this calculation is telling me.
Across all of the different attributes.
Across all of the different attributes. I have used every single attribute, so I have not left anything.
Except class.
Yeah, class is not an attribute, it's a response.
Yes, yes,
Yeah.
yes.
Okay, So what this is saying is that if I take a new row, a brand new row that's not already in my table, right? I can do this for all of the rows. I can get all of the distances, and I can find the 5 smallest ones, right? And look what's going on with those. Okay, so right now we are not going to go and find a new patient, right? What we are going to do is we are just going to use one of these patients. Before that, okay. So, distances, again, we're not doing details of code. It takes the training set, which is my historical data set, right? And the example, which is my new person, right? And it computes an array of distances between that new person and every single individual in my historical data set, okay? Then what closest does, closest takes the training data set, my new person, and my choice of how many nearest neighbors I want. Right? Because I just want to write one function that will do it all. Right? So supposing, so I can choose how many nearest neighbors I'm going to use. For now, let's just decide we're going to use 5 nearest neighbors. Okay? So what distances will do is it'll take my new point and it'll give me the distances between that and every single other point. Right? What closest will do, if I put in k equals 5, is it will find the points that have the 5 smallest distances. Right? Those are the 5 nearest neighbors. That's what it's going to do. So, you know, just give you, so distances gives you a table where the last column is called distance, right? And it's had all the distances. You sort by that column, right? So you get smallest, next smallest, next smallest, next smallest, and you take the top k. That's all that's going on here. Calculate the distances, put them in another column of the table, sort by that column, right? And now the first 5 rows are the 5 smallest distances, and you take those. That's what's going on here. So the point I'm trying to make is that the individual code is not that difficult.
And do the students actually do these codes?
The student,
at
yeah,
this point?
they're doing this along with me in
okay.
lecture. So when we go into lecture, unlike today, much of this is not already typed in.
Right.
Right? We are doing it in real time. John De Niro is brilliant at this. He never makes a mistake typing. Right? I am much worse. So if there is something that involves a lot of typing, I will usually have much of it filled out, but blanks in the places where the student actually needs to say, okay, this is where we're doing something, right? And so they help me fill in the blanks.
And let's be clear, you don't have to do live coding. That's just some way that they do it, but you definitely don't have to like.
Well, not today you don't. Okay, so I am going to, for no particular reason, take patient number 21 as my new patient. Okay? Okay, I'm going to take patient number 21 and I'm going to show you that person's attributes. Okay, so these are all of their attributes. Okay? And I'm going to try to pretend that this patient wasn't part of the historical data set, and I'm trying to go and try and predict this person's class. So, my historical data set better exclude this patient. Yes, I don't want that patient in there because they're going to be their own nearest neighbor.
Right.
Yeah.
Yes, I do not want this, right? So I take my training data set except this person, right? This is my person with their attributes, and I'm going to do 5 nearest neighbors. Okay? Okay. So I run this, and lo and behold, you have, for person number 21, these were the 5 people in the data set that were closest to that person. And you can see that the distances are increasing, right? All of the others, 670 whatever, were bigger.
Further, right.
Yeah? Okay. Look at the class column. What's your prediction for the class of this person? You're going to predict 1. Yeah?
This is amazing.
Okay. Yeah, it's a lot of fun.
I'm sold. I'm an ethnographer, and I'm like, this is just amazing.
Okay, so we now define a function that takes this table and returns the majority class. right? So the table has to do what you did by eye. The function has to do what you did by eye. It has to take all of these and return the one that's the most common. And now we do, okay, this classify. Classify is our function. What does classify do? It takes our historical set, our new person's attributes, and our choice of k. It is a one line. Give me back the majority class of the k closest points in the training data set to our example. Okay?
Did you set the majority? Are you calling that 51%?
No, it's an odd number. It's 5. Right? So
Okay.
there's always going to be a
For you.
majority.
Oh,
I
gotcha.
always take it. I always take an odd number.
Okay.
Okay, so I'm doing this. So we are now going to run our classifier. It says classify. Our historical data set is going to be all patients except this person that I have marked specially. The new point is this person that I have marked specially, and I'm doing 5 nearest neighbors. Okay? Classify. This thing should spit back a 1 or a 0. Okay? Okay, it spits back 1, which is exactly what you said it was going to do. Okay? Okay, now is the moment of truth. That person actually has a class. Right? And that class is in our original table. This patient's table just actually has the class at the end. All right, patient number 21. What is the class? The class is 1. We got it right.
Did
Right?
you pick that 21 on purpose, or was it random? Or do you want to answer
Let me
the
show you. Let me show you the next one. Right? So I have to pick some row. So I picked 12. I picked 21. I got it right. Right? I picked 12 just because I was messing with numbers. Right? I'm going to do the same thing again with person number 12. Right? So my example is going to be now person number 12. I'm going to classify that person excluding, of course, number 12 this time. Right? Same 5 nearest neighbors. And I am going to get a prediction of 0. Yes? The truth is unfortunate. I got it wrong. Okay, so now we're in this position where we know how to classify, and we have to see what fraction of time do we get it right. Can I take until 12:10?
Yeah.
Yeah, sorry to delay lunch.
There's sandwiches
but we're-
right there, but whenever.
Okay, all right. Yeah, I'm looking. See, you can't see the food, but
yeah,
I can.
she can see the food.
Yes. So, so my head is
No, go with
thinking
it.
about lunch. Okay.
Go with it.
Okay. So this is something that I have as part of my class notebook. Right? There are many steps in this process. So at this point we pause before we're going to do the next best thing, which is evaluating the classifier. We pause and we say, okay, what did we do? We figured out how to calculate the distance between arrays and then between rows, because all of our attributes are rows. We calculated all of the distances between a historical set and a new point. We calculated the k closest, we calculated the majority, and we put it all together in a function. Right? The student has a little bit of breathing room. They say, okay, this is what we have now done. And the key to having built this program little by little is that in the end you have this beautiful one-line program that gives you back the majority class of the k closest neighbors of your example point. Okay.
And this uses all the attributes.
This is using every single attribute. Yes. Okay, to classify a point, you find its k nearest neighbors, take a majority vote, and that's your prediction. So now you need to judge the accuracy of this classifier. And here, I mean, we are starting, I'm actually going to go back a couple of slides.
Wait, the accuracy of the classifier or the accuracy of the model we're using?
No, the accuracy of the classifier, but let me talk about the model.
Okay.
Okay, so this slide, I think, is not the right thing to start with. I will try to find. This one is the right thing to start with. In the end, there is a population of people about whom you want to make a classification, right? This is your historical data set for which you already know the labels, right? 0 or 1, right? You have a new person comes along and you are using this to make the classification, right? Forget what's going on there. Let's focus on here. If you want to classify members of this population, then your historical data set better represent this population. Yeah? Because if you are careless about that, no amount of computational cleverness here is going to give you a good prediction. For example, if you are trying to decide whether something, a picture, is a face or not, right? And you're going to test, you have a certain population in mind. If your sample set of faces only came from the people who are working in the tech company and their best friends, then you might just miss some faces, right? And then you have a problem. So while classifier accuracy focuses on here, in data 8 we start here. This is much more important. See where you got your historical data set from. And be aware that you can only make predictions for people who are represented by that. If you want to make predictions for a certain population, you make sure that your historical data set is a large random sample from that population. You have to work to get your historical set. Right? Otherwise, all of your predictions should come with caveats. Okay. So now assuming that you have your sample which is representative of this population, and here her clumps, I mean, we're just going to assume were representative of all clumps. I'm not a medical person, I don't actually know. Right? What we're going to do is say, okay, well, how do we figure out what % of the time we're going to get this process right? So what we're going to do is we're going to take our historical set and we're going to hide some of it. We're just going to say, I'm going to not use some of this. I'm going to use a portion of it to build my classifier, right? And then those bits, so those bits that I hid were not used in that development. I'm going to use those to test whether I got it right. I will not test my classifier using the same points that I used to train it. Yeah, I will use different points. So what's very commonly done is you have your historical data set and you set aside maybe 1/3 of it in the corner somewhere. Yeah, you just don't touch it. Lock it in a vault. And with the remaining 2/3, you build a classifier. And then when you have your function, you throw in your new points and see what fraction of the time you get it right. In data 8, we just split half and half. We are like this class at the end of our term, and we just don't want to get fancy. Okay, so that is what we're going to do, and that is what the slide says. Before we actually do it, I'll pause and I'll take questions. Yes?
So, I don't know whether, could you just choose, I know it's not an odd number, 100 nearest neighbors, then use that as the confidence? So
the more neighbors you choose, the more uniform your predictions are going to be. So supposing if I have, say, 275 data points, and I choose the 275 nearest neighbors, right? Then I will always make the same prediction, right? So you have a little balancing act to do. And we're going to change K when we run our thing, and you'll see what happens. It's actually not very easily predictable what's going to happen. Right? The best K, there's a whole world out there to decide that. Okay, so let's do this thing. Okay, so how many patients? We have 683 patients. We will take half of them as a training set, and we will take the remaining half as a test set. Right? We will build a classifier using the training set only. And then we will come along and throw in the first Wednesday. Okay, great.
Yes.
Okay, so I am going to randomly pick. It's really important that you choose half at random. and not the first half, because if you notice, my data set was set up so that first you got all the benigns and then you got all the malignants. So please, please, please randomize. Okay, so I'm going to choose a training set and a test set as random. Okay, and now we have a function that evaluates accuracy. It takes the training data set on which we are going to build a classifier. Yep. It takes the test data set. Now this is not just one example, it's a whole bunch of them, right? 341 actually, something like that, yep. For every point in the test set, it makes the prediction, 1 or 0, yep. And then it does what we did before, it actually goes to the original data set and finds the actual class and says, was it right or was it wrong? And then it tells us what % of time was it right. So for what % of individuals in the test set did we classify correctly? That is what we are going to get back. All okay? Right. So I'm going to define this function. And we are going to evaluate the accuracy of our classifier based on the particular training set that we got by picking 342 at random. Here we go. Chug, chug, chug. Got some work to do. 0.97. 0.97.
I have 0.97.
Yes, because your random training set was different from mine. Right? Remember, you picked half at random, right? You don't always get the same sample when you pick at random. So I got a half, I got a random half, you got a different random half, right? So you got 0.97, I got 0.967, right? Take a look at this. This is the simplest possible classifier, right? Very simple method. We didn't do anything. Nothing was weighted. We didn't do anything, right? 97% accuracy. Brittany Wenger did something a little more intricate, and she got 99%. But for absolutely no work, you're doing pretty well. Yeah. You might be interested in what happens if you change the number of nearest neighbors. Let me just do 3. So my training set and test set have been set already, right? I'm just going to use the same sets to do a 3 nearest neighbor classifier and evaluate the accuracy of that. Someday. Comparable. Right? So you can play with this all you want. You can put in 1 nearest neighbor, you can do whatever it is you want. What you have done is you have developed a k nearest neighbor classifier, and you have evaluated its accuracy. Right? So let's see what is involved. I won't go through the computational details, we've talked about that. But the big picture of what is involved is you're going to try to make predictions of the class of individuals in some population. You better have a large data set that represents that population, otherwise this method falls flat. Right? Why does it have to be large and representative? Well, representative because you're going to make predictions. Large because, first for representation, but also because you're going to split. Right? You're going to build your classifier on some fraction of it, you're going to test on another. You know, you would like both sets to be reasonably large. Yeah? And if you split at random and develop the classifier in this way, you have a way of evaluating the accuracy. Now, clearly, this is not the end of the story, this is the beginning of the story. But it is pretty much the end of Data 8. And when students go away, during these lectures, they are taking movie scripts and words that have been chosen from movie scripts. And they're using the words as attributes to classify the movies as romance or action. Right? So they are, as we are doing this in class, they are, for their assignment, their last project, they are classifying movies. And so their final assignment, when the lectures end, they turn in their classification of the movies and they tell us what accuracy rate they got. All right.
Sorry, one last question.
No.
I'm still struggling on the what we just tested as accurate. When you say the classifier,
Yeah.
so that was the kidney disease. Is
No.
that-
No.
This is not kidney. This is
Oh,
breast cancer.
Oh, Oh, was I getting my water? I'm sorry. All right, well, whatever.
Yeah,
So,
it's one of those.
I'm like, we moved diseases.
Yeah, we did move diseases. I apologize.
No, it's fine.
I started with
I
kidney
stepped
disease.
out. It's okay.
I went to bank
did
notes,
money.
and then I went to breast cancer.
Okay, I was here
Yeah.
for the fraudulent money. Okay. So it's the breast cancer is or isn't a good way to group the people in the sample? That's what you
So
just
what we are trying to do is predict. So it's our data are clumps of cells, pictures of clumps of cells,
Okay.
right? Attributes are numerical variables that have some technician has looked at the picture and given ratings to certain qualities of the picture. In our historical data set, we know whether those cells were benign or cancerous because they went through a biopsy process and it was known benign or cancerous. What we're trying to do is to say, supposing we now have a new person and they've just had their technician go take the picture and give these attributes. Just based on that, without doing anything more, can we predict whether they're benign or malignant, right? So that's what we're classifying. If we classify as a 1, we're saying malignant, and if we classify as 0, we're saying benign. Okay. So that's what the classify function does. If I give it a training set and a new example, right, then it spits back a 1 or a 0, which is my prediction. And that's all very well. So but now I have to see, okay, but you know, is this any good as a classifier?
Is your function good or is benign and malignant good?
No.
That's
Benign
right.
and malignant are just whatever they are,
Okay.
right? Is my function classifying correctly?
Okay.
Right? Now, to know whether a function is classifying correctly, I have 2 options. I can make the prediction, right? And then I can have the person go through various medical processes to actually determine whether that person's cell is benign or malignant and then compare. This takes a long time and it is rather intensive, right? So what we're going to do is we're going to take our historical data set that we have, right? And just see, can we build a classifier using that and use that data set to see how that, what fraction of time that classifier gets the right answer. So for this, I take my historical data set and I set a portion of it aside called the test set. I do not use that in my classification routine, right? I use that as the so-called new people, right? So I use the training set, the training portion of this, right, to build my classifier. Now I take every member of the test set and I classify it. Every member of the test set, the classifier gives me like a 1 or a 0. But you see, for every member of the test set, I actually know whether they're a 1 or a 0. Right? So I look at my predicted 1 or 0. I look at my actual 1 or 0. And I check, same or not. Right? And I look at the proportion of times they are the same. Because when they are the same, my classifier got the right answer. That proportion is what's being reported here.
That's the return them correct over that fraction.
Yes, exactly.
Okay.
Exactly. It's this number.
So a new patient that fits these
Thank you.
characteristics, you can tell the patient you may have cancer with 96% accuracy.
The doctor is just going to use this as one more.
No, sure. But based on
Yes, and we are going to say, look, the classifier says malignant.
with 96%.
No, the classifier says malignant. We are going to say exactly what the classifier says. The classifier says malignant. This classifier is accurate about 97% of the time.
Right.
Right? You want to bet on that? It's up to you.
And you
For
could go.
samples that
It's-
look like this.
Absolutely. For patients that we believe come from similar
Yes.
populations. That is very, very key.
And you could go through and test each attribute for its contribution to the prediction.
Oh yes, yes. You
For
could.
the
You could
classifier.
weight each attribute
Right,
by
you
its
weight each
size, its
attribute.
importance. You can do all kinds of
Yeah, you
things.
could also-
One of the things that students always point out is if I go back and look at where's my closest points? Okay, so here we just look at the 5 points that are closest, right? But we ignore the distances. Right? Maybe some points are very close and some points are quite far away, even among the 5 closest. So maybe you want to weight, like the closer points have more weight, so you can do that. Right? There are many things you can do. This is absolutely the simplest thing that you can do, is what we have taught the students how to do in Data 8. And if I think to my students when they come in on the first day and they have no programming and they have no mathematical background or anything, they're just engaged, curious, wonderful Berkeley students. And at the end of 14 weeks, right, they have bootstrap regressions and they have classified cancer cells. They learned a lot, right? And the thing is, they recognize they learned a lot. We have made it a mission to give them important problems to solve. One of the problems that statistics classes face when they are just using the hand calculator is first you have to, really condense the data down to them because the student can't, and there's a tendency to make up questions, right? There are 5 ducks and they have this average quacking sound or whatever. Nobody cares, right? So we have chosen examples we hope that students will care about. And they learn right from the beginning that they're doing things that are interesting and important, and that they all ought to be thinking about this stuff. Every single student in Data 8 ought to be thinking about that Supreme Court judgment that was made, right? Students should be thinking about how do you deal with privacy issues. Students should be understanding what it means for a machine to learn, right? And so we're trying to do this in the context of things that people care about, that students care about. And, what we need is collaboration with domain specialists. Right? Because I am talking about this and I am cringing inside because I have not one clue what I'm talking about. Right? I understand completely the computational and statistics theory, right? But somebody classified cells as cancerous or not, and so we need, collaboration. So I'm hoping that you will come to me with, okay, here's a data set, what can you do with this? Or, what you're talking about there, that's a little suspect. How about you do this better, right? And we would love, so that's one of the things that the class gets out of this every year, is we always have a colleague who comes and tells us, here's how you can improve. And so my request to you, before you all die of starvation, is that you please, please, please help us improve. All right, thank you so much for coming. Right, Eric? Lunchtime?
Lunchtime, and then the idea is,